Last time böyle görebiliyor musunuz arkadaşlar? Çünkü açılı fotoğrafta gece geliyor. He, anladım. Şunu şöyle yapmışlar. Vallahi becermiş arkadaş, nasıl becermiş bilmiyorum ama. Okay, last time we started talking about the correspondence problem, and we okay. So we started talking about the correspondence problem. We said that basically the correspondence problem is seeing which part of the given this point, which part of the other image corresponds to this part of the image, finding the corresponding part of it in the other image. Or I can ask the same question, given this point, what is the corresponding point in the other image? So if you solve this problem, you are solving the correspondence problem. Once you solve the correspondence problem, you know the disparity between left and right images. Okay. Left and right images. Once you know the disparity, you can plug in your disparity values to get the depth value for each point, or if you need more than the depth value, if you need the exact XYZ positions, then you know what to do. You know how to calculate those XYZ values using these formulas. Remember the reconstruction stuff? Get the correspondences, so XY values, the corresponding XY values for each image, and if you know the projection matrix of each camera, then you can get the XYZ values for those real world coordinates. So the problem here is finding the correspondence, and if you find the correspondence, the rest is kind of very well defined. But finding the correspondence is not a 100% solved problem. We can find the correspondence, the true correspondence solutions for maybe 95%. Thank you. For the 95% of the cases, but for 5% of the cases, we won't be able to do it very reliably. That's the artificial intelligence part of this stereo problem. Last time we talked about this. How do you compare two windows? We said that we can use this sum of absolute differences metric, or sum of squared differences metric. We talked about this, or we can use the cross correlation. And in fact, we had a very nice way of doing this cross correlation. We said that if you are comparing these two 1 to 5 by 3 window, that's a 15 element vector, and this 15 element vector, instead of comparing the elements one by one, we represent this window and this window like a vector, and try to find the angle between these two vectors. If the angle of these two vectors is the same, then we say that these two vectors are very close to each other. In fact, they are the same thing. If they are different, then that's the difference between these two windows. Okay, so each window is represented like a vector, and find the angle between them. That's what we are doing. That's called normalized cross correlation, and it works the best. Although it's a little bit expensive approach, it works the best in terms of local image correspondence establishment. And we said that OpenCV provides us a number of correspondence establishment procedures, and we looked at some of them. And I think that was it. At the end, we said that, okay, so far we have looked at the dense correspondence establishment method. What do we mean by dense correspondence establishment method? We mean this. We mean, let me go to the beginning of this. Okay. Given this left image and right image, finding the disparity or the correspondence for each pixel means establishing the dense correspondence. Okay, dense correspondence. Why do we call it dense? Because we try to find this, we try to establish the correspondence for each point in the image. Sometimes we say that this is nice. If I can find this dense correspondence for each image point, I can come up with this nice depth images or disparate images. That would be nice, but sometimes this may not be possible, and sometimes I wouldn't want this. In what kind of cases this is not possible? For example, if you look at this area of the image, okay, I mean, this is just flat, right? It doesn't matter if I look at this window or that window. I see exactly the same thing, okay? If there are no textures at the area where I am looking at, then establishing the dense correspondence will not be that easy, okay? For these kind of cases, maybe I am saying that maybe I shouldn't find the correspondence for these areas. Maybe it is okay to find the correspondence for these points, or these points, or these points, the corner points maybe, okay? Find the correspondence for the corner points or distinctive points, like the shift points, okay? Shift key points, or surf key points, and that kind of stuff. That's the idea of second set of correspondence establishment techniques. It is called feature-based methods, okay? With the feature-based methods, this is what you do. The epipolar geometry stays the same. We have the epipolar geometry. So what we would do is, okay, run some kind of a feature detector on my left and right image, and then find the correspondences between these features, okay? So that means what? At each epipolar line, instead of finding a correspondence for each point, I will find the correspondences for only detected feature points. Let's say I have 100 columns for this image, but for this line I have only 6 features. Instead of finding 100 correspondences for this line, I am going to find only 6 correspondences for each feature at most, okay? That's called the feature-based methods. And for the feature-based methods, of course, what do we have? We have, for example, if I am running shift key point detector, it will give me 6 key descriptors for this area, okay, for this line, and I will find the shift descriptors for the other line in the other image, and I will try to match those shift vectors or shift descriptors, and that will be as easy as that. So that's the feature-based method. It's not going to produce any dense correspondence, dense disparity map. It's going to produce sparse disparity map. But that's going to be enough for most of our applications. For example, if you are doing a robot navigation, it is okay to find the depths of the, for example, depths of the wall intersections. For example, the wall intersection between the wall and the frame of the door, or the wall and the ground and these chairs will be enough for me. Okay, I don't have to know the exact depth points of the ground pixels one by one. If I know the depth points of the nearby objects that I can collide with, okay, that should be enough for me. That's why we say that sometimes for some applications we don't need dense correspondences. Okay, and the other times dense correspondences are not possible, as I said before. I mean, if the images that I have are not textured images, if the images that I have are only images that contain lots of flat areas, then I can't do anything more than feature detection. And the other thing is this, okay? If I have a slanted surface like this, okay, the image of this surface on this camera is very different than this camera, right? On this camera, okay, I see this is a very long line, but for this one it's a very short line. So this SSD based or SAD based correspondence methods will not work very well, right? So in this case, I don't have my choice about using the window based correspondence establishment method. So what are you going to do? If I am lucky, I will get two features, or maybe this, okay, two features, one for this point and one for this point. And if I get two features, two shift descriptors for these points, I am going to match this one with this one, and I'm going to match this one with this one. Then I will get two correspondences, and that should be enough for me. Okay, maybe for the rest of them in between, I can linearly distribute these disparities between these 2 points. That's what I can do if I like to continue. Okay, so correlation-based methods, sometimes we don't need them. Sometimes I can't apply them because of these kind of purposes. Okay, good. So I think this is where we left 2 weeks ago. Any questions up to now? So let's look at this correlation, the feature-based methods. People said that, well, what kind of features should I use? Okay, I kept talking about using the shift features of the surf features, and they are nice. They are very distinctive, but they are not very dense. Okay, for each epipolar line pair, maybe I will get a few shift features. Okay, and a few of them is not enough. So what are we gonna do? They have suggested this. They said that why don't we use the edges? Let's go to the same picture again. Okay, do the edge detection, and on this line here, on this line, and on that line, okay, try to match the edges. And if you look at this, I'm trying to draw the edges using a different color. Maybe green is good. Okay, there is an edge here, there is another edge here, edge there, right? So as you see, many edges, and there will be lots of more edges if the thing is textured. Good. So as you see, it is not as many as a dense disparity map, but it is pretty dense. But how am I going to match these? I mean, these are just edges. These are just edges, and matching two edges, I don't have many ways of matching the edges, because edges are just edges, binary stuff, edge or no. Maybe I can use some other properties of it. Maybe I can come up with a smarter way of matching the edges. One suggestion is this: don't run your edge detection. Don't run your edge detection on this whole image. run your edge detection on a smoothed image. Okay, so ignore the details first. If I smooth this image, okay, and make it smaller, my edges will not be visible for these kind of details anymore. My edges will be, for example, this will be an edge, this will be another edge, another edge, another edge. All the rest of the edges in between them, they will be gone if I smooth the image first, right? Smooth the image first, find the edges, do your correspondence between these smoothed edge pairs. Once you are done with these smoothed edge pairs, modify your images so that, or shift your images so that the corresponding points lay on top of each other. Then do another level of smoothing, but this time not as much as the previous one, and continue it this way. Let me give you one example directly from the book. Okay, it's called multi-scale edge matching. This is what we mean. Okay, I smoothed my images, left and right image. Okay, instead of seeing the details, I just see two blobs on the left and right. See that this left image is not exactly the same as the right image. See the gap between them, because I have to. So I know that I have detected this edge, another one, and four of them are here too. And I can match them. Once I match them, okay, if I put these two images on top of each other, they will not correspond to each other, but I know that this one will match to this one will match to this one. So after I establish correspondence, I can move this blue one towards the red one, so they are sitting on top of each other. Okay, after doing that, after doing the matching and doing the offsetting, okay, I can use the less smoothed image and run another edge detection, and this time do the matching in a very close by region. Okay, that's called multi-scale edge matching. I don't do a single edge matching, I do many edge matchings in a hierarchical way. Okay, so first I run a smoothing filter. Okay, then do the zero crossing. Well, instead of doing that, let's do the Laplace of the Gaussians. Remember the zero crossing edge detector operator? It uses both the edge detector, it does both the edge detection and the smoothing at the same time. Remember that? The Mexican hat operator. So use a large sigma value, get your edges, establish your correspondences, take the offset out, use a smaller now, do the same thing, use a smaller now, do the same thing, and at the end use a very, very small sigma value, so you don't lose the edges, no edges at all, and this will be your final establishments. Okay, correspondence establishments. Okay, so this is called the multi-scale edge matching, and this multi-scale processing is used a lot in many computer vision problems. Do the matching at a very coarse scale. Sometimes we call it coarse to fine. Coarse to fine processing. Sometimes we do this for stereo, sometimes we do this for motion, sometimes we do this for object detection, and etc. Solve your problem approximately on a coarse image, smoothed image. That will get you the general structure of your problem. Then work your problem on a finer level image, coarse to fine approaches and multi-scale approaches, and this is a multi-scale approach. And in fact, if you remember the SIFT descriptor, it is done that way too. We look for the correspondences or we look for the feature stable points at very coarse levels, then the finer levels, etc. Okay, so this is called multi-scale edge matching. Good? Any questions? Okay, let me continue then. And then last time maybe I talked about this a little bit. Maybe I should, I'm not going to go into detail, but just to remind you what we said. We said that if we have an object like this, a circular object, a spherical object in the 3D world, I have these 3 points A, B, and C. Doesn't matter what point, doesn't matter at what orientation you are looking at this object. The ordering of these small a, small b, and small c, a prime, b prime, c prime, their order will not be different. Ordering will always be the same. If you have a continuous surface, okay, this sphere has a continuous surface, it will be always a, b, c, a, b, c. So you have to keep the ordering constraint, okay? So why are we talking about this right now? We are talking about this because if I am going to establish correspondence, between left and right images, if I say that A prime corresponds to A, then if I say that C prime corresponds to C here, I know that this B has to correspond something between C prime and A prime, right? That's if I like to keep the order, okay? If I like to keep the order. So that's the ordering constraint that would give me lots of good constraint on my correspondence establishment problem. So that will be nice. This correspondence constraint is only valid if you have a continuous surface. But if you don't have this continuous surface, for example, ABC is a continuous surface, but D is another surface. Okay, there is a discontinuity. In that case, see, the order is A, B, D. Then this is one D, B, C. So D and B are changing orders, right? So if you don't have a continuous surface, this constraint doesn't hold. Assuming that I have this continuous surface constraint available. I know that, let's say I am looking at a face of a person. The face of a person is a continuous surface. I know that. And I like to do the stereo correspondence on that one. How can I use this constraint? For that one, they have this dynamic programming based method. Let's see. I think I looked at this image, but I didn't have much time to talk more about it, and I'm going to do it right now. Let's say again. I will try to do the exact same thing. I don't know how am I going to do it, but maybe I will do it this way. Where should I draw it? Okay. I should see it that way, and okay, I will try to do it here. Okay. Let's say I have my, again, two-dimensional world, one-dimensional images, just to make them simple. My left camera and my right camera, and on my real world object, I have such a surface. Okay, this is my surface. Surface should be maybe green. There is a straight line here. Okay, so this straight line will be, make it smaller maybe. This straight line will be visible on both left camera and right camera. Why? Because I can do this, right? I can do this. My left camera and right camera sees it. Okay, so this point, this point, this point, and this point. So this surface is visible on both of them. I am trying to do the same thing. Okay, so for my points 2 and 3, my left, okay, this is going to be my left camera and right camera. My left camera sees it, but right camera doesn't see it. How am I going to do that? Okay, how am I going to do that? I think it will be something like this. So this surface, right? This surface will not be visible. Maybe I should do it a little bit like this. Okay. This surface will not be visible from the right camera, but it will be visible from the left camera, right? So if I try to draw it, is somebody asking a question? No?
Hocam Teams'te ekranı gözükmüyor ama.
I don't know what's happening with the team, sorry. I don't know, I shared my screen. It is being shared right now. I cannot stop it and share it again. Okay, so it will not be visible on my right, but it is visible on my left. Okay, because if I try to, because I am seeing the back side of this surface. Okay, so this will correspond to this point, and then I have this continuation. It will be visible for both of them again, and then what? And then maybe a little bit slanted like that. It will be visible for the right and left, but it will be more visible for the right. And then I have this. This time this will not be visible from the left, but it will be visible from the right. And then this. Okay. So this is my left and right cameras. Let me try to let me try to do it a little bit better. Okay, delete it. Okay, delete those two. Okay, so this is my left camera, sorry. This is my right camera, and these are my points. 1, 2, 3, 4, 5, 6. Okay. So this is a continuous surface. Okay, and if you look at this image, it is the same thing. So left camera, I see between 1 and 2, right? I see between 1 and 2 for the well, I think I changed it too much, right? So this 1 and 2 is not visible from, yeah, I think it is too much. This is too much. I see it. Maybe if I move it out, let me try to move it out like that. Okay, so between 1 and 2, I am seeing it on my right camera. 2 and 3 is not visible from right, but from 1. This one is visible for both. This one is visible for both, but this one is not visible for left one, and this one is visible for both of them. Okay, so what I am saying is that, okay, this part here is not visible for the right camera, and this part is not visible for the left camera. The others are visible, but somewhat, some of them are longer, the others are not long. And on a continuous surface, I have these features. On a continuous surface, I have these features, and I say that my order and constraint is valid. But sometimes I see one of them, sometimes I don't see the other one. So I shouldn't change any orders. Okay? So people said that this problem is matching these points to points is exactly the same as this edit distance problem of the matching two words written in a different way. Let's say I am typing a word execution, but in fact I wanted to type intention. I am asking you this question. what are the minimum number of keystrokes that I can change this execution to intention? Okay, so they say that you can solve this problem by dynamic programming. How? This is what you are going to do. Okay, the cost of changing nothing to nothing is 0. Okay, the cost of changing nothing to E is 1. The cost of, okay, because we are just adding an E, the cost of changing I to 0 is just 1, because you are just deleting I, and the cost of changing I to E is just 1, just replacing 1. So this corner solve the problem of matching the key E with I. So you are saying that if you like to, instead of writing E, if you are like to write I, your cost will be 1. How about this one? How about if I like to solve the problem of doing this? Okay, changing into EX. Okay, and by the same thing, you are saying that it's going to be 2. By the way, when I add this one, when I add this part, only this part, okay, only this part, I calculated this by just checking the neighbors, okay, just checking the neighbors. So I have already used the already calculated points. So matching 2 letters with 2 letters. And if I continue doing this, expand it a little bit more, okay. Now I am talking about these three letters, okay, matching them, exe to int. So if I continue this way, at the end I am going to get this letter, the cost 5. That cost 5 will tell you, what is the cost of matching this execution with intention, and 5 also will tell you how many keystrokes you have to do to do this editing between these two words. Okay, this is straightforward dynamic programming, and you know this from your algorithms course. Okay, and I can do exactly the same thing with this problem. Okay, I am going to match these 6 points on my left image to these 6 points on my right image. These are the detected points, and these are the detected points, either edge points or the serve points, doesn't matter. By the way, these numbers doesn't have to be the same. This could be 6 and this could be 17, doesn't matter. I like to find the minimum cost path from this corner to this corner, and this one says that 1 matches to 1, 2 matches to 2, 2 also matches to 3. That means what? These 2, 3 segment is not visible from the right image. Okay, and if I have a diagonal line, then that means that it's going to be visible for both of them. If I have a vertical line, this one doesn't see it. If I have a horizontal line, this one will not see it. Okay, so if you draw such a line from one corner to the other corner of the image, then you are establishing your correspondences, and that's going to be a very nice solution that will handle your missing points. One of them is occluded from the other one. As long as the ordering constraint is satisfied, then I am fine. This will work on this kind of images, but not on this kind of images. Okay, so usually we have, for example, if you have a satellite from the space, if the satellite is taking pictures, from the space, the Earth surface is a continuous surface, right? There are no discontinuities. It's either mountains or the flat areas or the sea or that kind of stuff, right? There is no discontinuity on the Earth, okay? If you look at from the Earth perspective, and if you ignore the clouds and that kind of stuff, we can ignore them, and it's going to work perfectly for the satellite images. Okay. By the way, satellite images, they take stereo by doing this. Let's say this is the Earth, okay? This is your satellite, is a large camera. It is looking at Earth in this direction. Let me rotate it a little bit more. Okay, and these are your mountains and that kind of stuff on the Earth. And this is your satellite looking at your Earth that way. Okay, let me change it a little bit because, okay. So the satellite is looking at the Earth this way, and it is in orbit, and it rotates. Okay, it orbits around the Earth that way. So it takes these images from this angle. When it moves to this position, okay, it immediately rotates itself to this position. Okay. So what do you have? You have two sets of images of the same region. Okay. So it makes a very nice stereo pair, and the baseline is maybe 300 kilometers. Very nice baseline, and this length is maybe 300 kilometers. Okay, very nice depth, and using this you can get the three-dimensional structure of the world, or the moon, or the Mars, or whatever you are looking at, right? So our observation satellites, Turkey has two of them, and we are sending another one very soon, maybe send, I don't know. And they scan the Turkish landscape. First they come it this way. After this is Turkey, right? They scan Turkey from this angle. As soon as they pass on top of Turkey, they just reoriented themselves, and they get the second set. Okay, and they have the stereo setup. Of course, you might say that, well, I mean, there is a difference between, I mean, this is at time t, this is at time t plus 100 minutes or seconds. This is not stereo. There is a, I mean, on world surface, you don't see much change in just 100 seconds or 100 minutes, right? Unless there is an earthquake or something like that. Okay, so it works. So this one is very valid. This one is a very valid algorithm for those kind of constraint problems, and it works very well using dynamic programming. It's very simple, cheap, and it works. And one of the OpenCV implementations uses this ordering constraint. Okay, good. A question for you: if the ordering constraint doesn't hold, what would you do? I don't want to give up this algorithm. This is a very nice algorithm, and I know that in my cases there are situations like those. What would you do? Let's go to the first example. Question for you first. Does the ordering constraint hold for the scene? The answer is no. The same question again. Does the ordering constraint hold for the scene? You are going to say no. Say no.
No.
Okay, why? It is easy to say no, and you know that, right? I'm going to ask why. Ordering constraint holds for this part of the image, right? It holds there, right? Ordering constraint holds for this part of the image. The problem happens around these regions, okay? Here, the ordering constraint here and the ordering constraint, it might be different because there is surface discontinuities in there, right? So maybe the solution would be find the surface discontinuities, and say that I am going to run my dynamic programming based algorithm on this region and on this region. Okay, and that will work fine. Beyond that regions, I am going to run other dynamic programming based stuff. Okay, so definitely, I mean, this ordering will not help in here. See, this, let's look at these. This point A, or choose a different color. This point A, B, C, and D, A, B, C, and D, and here is going to be A, C, B, and D, right? So definitely a different ordering because there is a surface discontinuity. Okay, so maybe you can find these kind of solutions to your problem. Okay, it will not be as elegant as the original solution, but it will be better than doing nothing, right? So, which method should we use? Dense maps or the feature-based maps? Okay, depends on your data, depends on your application. Okay, dense maps are good for surface reconstruction. If you like to reconstruct the whole surface, then dense maps are good. Then you should do it. But the dense correlation-based methods, the windowing-based methods, correlation-based methods, windowing-based methods, okay, they will not work if you don't have textured images. If your images are all flat, it will not work. Okay, it will not work. And they are sensitive to illumination variations. If your left image and right images are very different brightness, and we are sensitive to it. Okay, and if your viewpoints are very, very different, then it will not work either. And feature-based methods they are sparse maps. They are not good for surface reconstruction, but they are good for navigation. Okay, and we need to run some kind of a feature detector first. This one doesn't require any feature detectors. Okay, good. We don't say that one of them is better than the other one. We say that it depends. Okay, if you have good textured images like the Earth images from up above, then you are fine. Or some medical images, usually we have textured images. But for flat stuff, for human-made stuff, for example, the buildings, internals of the buildings, this correlation-based stuff doesn't work for that board, for that the wall or the ground. We have very uniform image data for those. Good. Any questions? Did everybody sign this attendance sheet? Okay, let's take 15 minutes of break. After the break, we will continue 15:35. We will continue. Ha?
Diğer kağıt var mı? Ha, tamam.
Kağıtlar ne?
Bundan sonra da dersin var mı?
Bundan sonra yok ama bu dersin daha çok var.
Ne kadar çok var?
2,5 5,5.
Ey maşallah.
Sen git ya.
Gidelim.
Kendini pet al.
Hayır.
Niye?
Orada dursun, gelenlere ver, tamam mı? Yoksa bana getir. Ha, gelenler olursa uzat onlara sen. Okay. So that will be end of this discussion about the multi-view geometry. We will come to this topic from time to time because this is related to motion. This is related to some other geometry related stuff. But that will be basically it. If there are no questions, I will start a new topic, which is camera calibration. Any questions? Okay. So, geometric camera calibration. There are other camera calibration procedures such as photometric camera calibration. We are not going to talk about it. We are going to talk about geometric camera calibration. And if you remember, this is our projection matrix. Our projection matrix is a 3x4 matrix that transform our three-dimensional world coordinates into two-dimensional image coordinates. It's a linear operation, as you know, matrix multiplication. And the camera calibration means finding the elements of these matrices: translation matrix, rotation matrix, and the intrinsic parameters. These are extrinsics, and these are the intrinsics. That's the definition of the geometric camera calibration. Remember, we multiply, given a three-dimensional world point with M, we get the homogeneous coordinates of the image coordinate M with P on the other end, and finding the well, this is projection matrix, right? This is projection matrix. Finding the projection matrix is different from finding the elements of these three matrices. This is a 3x3 matrix, 3x3 matrix. This is a three element vector, right? So if I multiply these three, okay, I will get a 3 by 4 matrix. Okay, this is a projection matrix. If you find the projection matrix, that doesn't mean that you automatically found the calibration parameters, because I mean if you know the calibration parameters, you can definitely get the matrix M. You just multiply them. But going from this direction to this direction is a little bit tricky, and that's what we are going to do in this chapter of the book, Calibration. For this, we are going to use lots of tricks. Most of them will be based on this. Remember, R is the rotation matrix, right? What are the properties of rotation matrices? It is this. If you multiply R with the transpose of it, you are going to get the identity matrix. That means what? That means inverse of R is equal to the transpose of it, right? That's something that we are going to use all the time. We are going to use it all the time when we do the camera calibration. So don't forget about it. And if you think about it, actually, if you think about it, R is a 3 by 3 matrix, right? 1, 2, 3 numbers, and 3 numbers here. And let's say this is R, let's say this is RT. Again, maybe I should do it this way. Second row and the third row. If I take the transpose of it, it will be this one, and blue is this one, and gray is this one, right? And if I multiply these two, I would get 1, 1, 1, 0, 0, 0, 0, 0, 0, and that will be the output of it, right? So what does that mean actually? It means if I multiply these three blue stuff with these three blue stuff, which is the same thing, it will produce me a 1. But if I multiply these three blue stuff with these three green stuff, it's going to produce me a 0, right? So that's the meaning of this R times RT equal to this. Okay, that's the definition. That comes directly definition of the orthogonality. Okay, so we are going to use this feature a lot. Good. Okay, so let's move on. Let me get rid of my markings from the previous year. I can write them all the time. Anyway, okay, good. So camera calibration is the estimation of the camera parameters, intrinsic, extrinsic, and both. Sometimes I can say that I am going to give you the intrinsic parameters of a camera. Find me the extrinsic ones. Okay, that's a very valuable tool actually. If I know the intrinsic camera parameters, that means if I know, let me write it again. M is K R T. Okay, if I know K and I like to find R and T, okay, that's again a camera calibration procedure. It's a simplified one, yet it's a camera calibration procedure, and that's a very valuable procedure to find it. And in fact, let me show you this. Let me show you. What do I show you? Let me show you. Yeah, somebody did this demo. It's a nice demo. This guy is, okay, he previously got his camera's intrinsic parameters, okay, and now he is doing this live demo. He shows this calibration pattern to the camera. He knows that this is a 1, 2, 3, 4, 5, 6 by 1, 2, 3, 4, 5, 6, 7, 8. 6 by 8, okay, checkers board. It knows that. It finds these corner points using the corner detector or any kind of feature detector. Okay, it knows on the image and in the real world where these points are corresponding to. Okay, and it knows the intrinsic camera parameters, and every time when I find these extrinsic camera parameters from each frame of this video, I can find my extrinsic camera parameters. Once I know my extrinsic camera parameters, I know where my camera is with respect to this checkerboard, and I can do this animation then. Okay, every time I am drawing my checkerboard with respect to my camera, and when I move this checkerboard to relative to my camera, I can do the orientations and everything. So this is all possible because I already know the intrinsic camera parameters. I have full control of my virtual world, and I can do this. Okay, so this is done using the solve PNP, OpenCV function solve PNP. Let me show you how it works. OpenCV solve PNP. Okay. Post computation. Post computation means that finding the, okay, basically say that if you give me the corresponding points between the real world coordinates and the image coordinates, I can give you the rotation and the translation components of your camera. Okay, RVEC and TVEC. Once you know those, then you know your camera's pose, the relative translation and rotation between the real world and your camera. Okay, so solve PNP does that. Okay, it gives you those values. Once you know those, then you can do those kind of animations. You can say that I know all of them. I know K, I know R, and I know T. I can project all the points to the real world, and I can get those kind of animations. Okay, just read this, and it has many different overloads of it, different ways of solving the K and R and T matrices. I'm not going to look at this one in this lecture. I'm going to show you how to solve all of them at the same time, including the K matrix, intrinsics and extrinsics. But okay, these are just, I think I will come back to this one when we do the motion later. Okay, back to the camera calibration. Again, the definition of camera calibration is finding the intrinsic, extrinsic, or both of them. And we need the camera calibration because if you know these K and R and T, that's the kind of application that we can do. Okay, knowing your camera position with respect to the world, okay, is going to give you lots of stuff, especially if you are going to make some adjustments, make some measurements in your real world. Okay, so this is the basic setup that I'm going to use for this chapter. You don't have to do it this way, but I mean, OpenCV has a very nice way of calculating or estimating the camera parameters, all of them. It is not as restrictive as this one, but this one is a simpler way of telling you how to do the camera calibration. So you are going to need a target like this. This target has 3 perpendicular planes. Okay, this one is orthogonal to this one, and this one is orthogonal to this one. So there is a 90 degree. There is a 90 degree angle between these two planes, and there is a 90 degree angle here, and there is which is the third one? Third one is this one here. It is here. So all of them are perpendicular to each other, and I assume that this point will be my 0, 0, 0 point in the real world. Okay, and our I direction, J direction, and K direction. And I know that each square is like 1 centimeters. Okay, 1 centimeters. So this is a point here. This is a point is this is 1 0 1, okay, and this one is 1 1 0, right? 1 1 0. Okay, so these are my real world coordinates in terms of centimeters, or you can say 10 0 10, or in terms of millimeters, okay, 10 10 0. So I know the positions of these in the real world. If I take a picture of this setup using this camera will produce me an image like that, and in that image I will have this lines like those, right? And they will be like those. And I know that this point will correspond to 0 0 0 in the real world, but in my image coordinates this one will correspond to column number 50 and row number maybe 30, right? And this point will correspond to column number 70 and row number 25 maybe, right? So I know that this one will correspond to real world point 0 0 0, it is 50 30. This one 70 25, and it will correspond to, for example, 20 comma 20 comma 0. Okay, so I have lots of correspondences between the real world points to image points. For I of them, I will be from 0 to some large number, maybe 30, for 30 of them. Okay, if I know these, then how do I connect each pi with small pi, okay, through the projection matrix M? Okay, so each correspondence will give me something about this projection matrix M. Inside the projection matrix M, I have 12 unknowns, right? I have 12 unknowns. If I have 12 equations, okay, then I can calculate this M, and I can find the projection matrix M. So all I need is just 12 correspondences, maybe more or less than that, because each correspondence is producing 3 equations, right? Do you remember that? This has 3 rows and this has 3 rows, and each row is a separate equation. So that means that just 4 different correspondences between the real world and the image coordinate system should produce these matrix M, but usually we need more. We like to include maybe 30 points, so that we are robust against the noise and calculation errors and the lens related distortions and that kind of stuff. Okay, so that's the idea, to calculate this projection matrix M. But again, as I said before, calculating N or estimating M doesn't mean that you know K and R and T, because this is M is multiplication of these 3 matrices and vectors. Okay, so we need to recover those parameters to get the values of K and R and T, and I'm going to show you how to do that. Okay, let's look at how to get this matrix M first. Okay, so assume you have n image points, ui and vi, and corresponding n world points in homogeneous coordinates. I can write these M as this one. Then after estimating this, we are going to estimate the intrinsic and extrinsic parameters, which are these. Okay, you remember this? It looks very, it looks very complicated, but you know it is not complicated. Again, let's remember how many parameters we have in there. So this is a 3 rows, row number 1, row number 2, and row number 3. Okay, and how many columns? 4 columns. This is the last column, and inside this matrix there are 3 by 3. Well, as you see, this is just a column. Okay, TZ is just the third component of our translation vector. Okay, TZ is the translation component of the third component of the translation vector. This one says that let's try to remember this one. Tz is the third component of the translation vector. How about V0? What is V0? U0, V0. You guys remember it? It is called what point? It is called if this is my center of projection, okay, and if this is my image plane, and in center of projection this is my XYZ, this is 0, 0, 0. The x-axis that intersects with the image projection, okay, this is U0 and V0, okay, this is the principal point. Remember? This is the principal point. So U0 and V0 are two principal points. We know those. How about this theta? What is theta? Theta is, you don't remember anything?
The angle of camera itself.
What?
Was an other angle the camera.
It's an angle, right? What kind of angle is this? Yeah, it's kind of an error. Well, we wouldn't call it error, but we like this theta to be perfectly 90. If it is 90, then this becomes just 9, and this becomes, you say, I mean, if this is just 1, then it is just beta, right? So what is theta then? Theta is the angle of our image plane of axis, okay? We like this angle to be perfectly 90 degrees, but usually it is not 90 degrees. So this angle is our theta, skew angle. That's the theta, okay? We know that. How about alpha and beta? Alpha and beta are the parameters that correspond to okay, this is alpha and this is beta, the pixel width and pixel height of our images, okay? These are alpha and beta. What else? We talked about alpha, beta, theta. Tx, ty, tz are our translation vector between the camera coordinate system and the real world coordinate system. Okay, so tx, ty, and tz is a vector t. Okay, we know those, we talked about those. How about this, these r's? R1, R2, and R3 are our rotation matrix. It has 3 elements here, right? 3 here, 3 here. Okay. If I take this vector and if I call it R1, take this one, this is R2, and this is R3. So R1 is the first column of the rotation vector matrix, R2 is the second column, and R3 is the third column. Here I take the third column of this rotation matrix and transpose it, so it becomes a vector like a row vector like this. So 3 elements in here, right? So there are 3 elements in there. It is called R3 transpose. How about this one? Beta over sine theta times R2 transpose V0 times R3 transpose. So this is a 3 element vector. Again, 3 element vector in there. So these are row vectors, 3 of them. So this whole area is a 3 by 3 matrix, and this one is a column vector. Okay, good. So this is M. Okay, this is M. By using the procedure that I told you before, okay, if you calculate M, what you're gonna get is just 12 numbers. And by looking at those 12 numbers, you can only know this TZ value. and this R3, the third column of the rotation matrix only. The rest of them, I don't know, because this one will give it, this is a number, you get that number as an element of M, but that number will tell you only very little about V0, TZ, TY, beta, or sign, because these are just multiplication and additions of those values. So it is our task to go back and calculate those values. Okay, we are going to do that. Okay, good. Okay, let's get started. This is what we are going to do. Okay, I know this one, K times R times T is equal to M. If you multiply, if you divide those values with the, remember that this P has three components, X, Y, Z. Because of the homogeneous coordinates, if I divide this by Z, you get the two-dimensional component. And what I'm saying here is that this is what you do. Multiply P with the first row of the projection matrix and divide it with the third row, which is that Z. You get the U component, X component of the image coordinate system. And do the same thing. You multiply P with the second row of the projection matrix and divide it by the M3P. You get the V component, X and Y. Okay? X and Y. We know those. So, which ones are the knowns? Okay? Which ones are the knowns in these equation set? Linear equations. Do I know U's and V's? You're going to say yes. Yes, you know them. Why? I told you how. I told you that. I told you that. Okay. U's and V's come from this image. X, Y, Z's come from this target. Okay. I know U's and V's. How about those P's? Of course, I know the P's too. Okay. And these are the things that I don't know. M1, M2, and M3. Those are the things that I don't know. So let's do some algebraic procedures. For each of those, I can write these, right? M1, okay. M1 minus UI M3 times PI is equal to 0. You understand that, right? How do you know that this is a scalar? Well, M1 is a, what is M1? M1 is a row vector, okay? A row vector of 4 elements. This is a 4-element row vector. Multiply it with a scalar and take the subtraction and multiply with this pi. Pi is the homogeneous representation of three-dimensional point, and if I multiply these three vectors, then I would get a 0. So what that means, what this vector and this vector is orthogonal. This vector and this vector is orthogonal. Okay? It looks it's going nice, but the thing is that these are known, these are not known. So what am I gonna do? I like to take this out and put it in a shape that it is like this. Okay? P times M is equal to 0. There is a 0, right? P times M is equal to P is this, and M is this. The first row, second row. Okay, this is the first row of the projection matrix, second row of the projection matrix, and third row of the projection matrix. But I put them as like, okay, this is like 4 of them here, 4 of them there, and 4 of them here. Okay, M1 is here, M2, and M3. So this is a 12-element vector. Okay, so P times M is 0. So tell me the size of this matrix. How many rows and how many columns? How many columns? Maybe it is easy to say. How many columns are there in this matrix? 12, right? Because M is of size 12. So there are 12 columns and how many rows? How many rows?
And
Not n, but 2n, right? Because for each correspondence, I have two equations, right? I have two equations. So there are 2n rows and 12 columns. What is n? N is the number of correspondences. Okay? N is the number of correspondences. So I know all the numbers inside this P. Okay? And there are 12 unknowns. That means what? 6 correspondences should be enough. But I am going to use much more than that. I am going to use much more than that. Okay? So it is going to be like this. I know these values inside this one. This is a n by 12 matrix, and this is a 12 element vector, and I am going to multiply these, and I'm going to get zeros from the other side. Okay? I know all these p's. I don't know these m's, these 12 numbers. Question for you. If I find this solution, if I tell you that I found your solution, it is m prime. Okay? And m prime has numbers like 1.2, 7.5, 12 numbers. Okay? If somebody tells me that if this is your m prime, then 5 times m prime is another solution. Is that correct? Answer is yes. Why? If m prime is a solution to this problem, then 5 times m prime or k times m prime is another solution too. One last time I'm going to try this. Did you find the answer? Never. This is the 15th time I am asking the same question, and I think somebody should tell me the answer to this.
P times m equals 0, right? The equation P times m equals 0.
Yeah,
So we can divide any scalar number.
yeah. If this equation is equal to 0, it doesn't matter if I multiply it with k on both sides. As long as I multiply it with the same k, it will be the same thing. So what I'm saying is that, okay, if somebody says that this is my projection matrix, I can find infinitely many projection matrices by multiplying that projection matrix with another k, right? That's what I am saying. Okay, that's what I am saying. Or maybe I can ask you this question. By looking at this equation only, nothing else, this equation only, just look at it. I know all the values of P. I don't know the values, any of the values of M. Just tell me, give me an answer just right now. Without doing any calculation, you just can tell me one solution exactly. You're going to tell me that if M is this, yeah, if m is 0, if m is exactly 0, 12 zeros, then that's the solution, right? But we call that solution a trivial solution. Trivial solution, and we don't like the trivial solutions. I mean, we are after another solution. We are looking for another solution, and that solution should not be a trivial solution. Okay? What is wrong with M0? Well, it's a solution to this equation, yeah, true, but That's not good for me. I'm looking for a more reasonable solution. So we need to find ways of it. If you use a standard matrix solver, for example, the Gaussian elimination, right? Gaussian elimination will give you exactly 0, 0, 0, 0, 0. And I don't like it. Okay? I need to find a more useful solution than the trivial solution. And you might say, how do you know that there are other solutions to this problem than the trivial solution? Well, I gave you all the equations, right? The intrinsic and extrinsic. It makes sense. Okay? So, your solution of the trivial solution doesn't make sense to me. Okay? But maybe you didn't see this kind of a mathematical equation not giving you the exact solution that you want, but it happens in mathematics. Okay? Sometimes your equations produce many solutions, and you don't like some of them. You say that I don't like this solution and this solution and this solution. I am going to find other solutions. So in this case, map is maybe a little bit relaxed than our problem. We cannot model our problem with exact mathematics. Okay, maybe the mathematics is modeling our problem a little bit more relaxed than it needs to be. So we cannot make it tighter. So we are going to deal with it using our problems. Find all the solutions. Ignore some of them, use only these. Okay, good. Okay, so that's what we are going to do. For that, I need to introduce, well, maybe I need to remind you some stuff from your linear algebra course. Singular value decomposition, you remember this? Singular value decomposition. Tekil değer çözümlemesi. Ayrışımı, tekil değer ayrışımı. Singular value decomposition. I am sure. What kind of decompositions did you see in your linear algebra course? LU decomposition, triangulation, LU decomposition. LU is lower part, upper part decomposition. You have seen, I am sure you have seen it. Maybe you forgot. Because you seem like you forget everything, even I told you from last week or 2 weeks ago. Okay? So I am not expecting you to remember all that stuff. I am just going to remind you. So a few slides about the reminder about the singular value decomposition. Given any matrix, okay, m rows and n columns, okay, m by n matrix, you can decompose this matrix into three matrices, U, D, and V. U, D, and V. Here I take the transpose of V and multiply it together, and you get this A. We say that our D matrix is a diagonal matrix. What's a diagonal matrix? Only the elements of the diagonal line here could be non-zero. All the rest has to be zeros. Okay, so this part, this triangle here, it has to be all zero. This triangle all has to be zero. This diagonal, okay, could be non-zero. Of course, being zero is a possibility for that diagonal too. But other than the diagonal, everything has to be zero. And these are our, okay, singular values. Okay, and singular values are very important features of a given matrix. They are fully determined by a matrix. They are important, and these are, why are they important? Because they are related to the eigenvalue problems that I told you before, and I'm going to show you how. Okay, some features of it. These are just definitions. I mean, they are not definitions. They can be proven, but I am not going to do that, of course. I'm going to tell you what they are. So these singular are values by the feature of the singular value decomposition. Sigma 1 has to be greater than or equal to sigma 2, and sigma 2 is greater than or equal to sigma 3, and it goes like that. And sigma n has to be greater than or equal to 0. So they are all non-negative values. Okay, sigma n could be 0, n minus 1 could be 0 again, or sigma 1 could be 0 too. But usually for nice matrices that can give us some solutions, they are non-zero values. Okay. U and V matrices are not unique. Depending on how you do the decomposition, U and V could be different, but I know that the columns of U and V are orthogonal. So if you multiply this column with this column, you are going to get 0. They are orthogonal. If you multiply this column with this column, by the way, since this is VT, this is the transpose version of the V, okay? So they will be orthogonal. They will be, maybe when you multiply them, they will produce a scalar 0. Okay? Columns of which are mutual orthogonal vectors. Okay, good. So some features, nice features, but I mean, you might say that, so what? What am I going to do with these features? And I'm going to tell you what you're going to do. Okay? There's singularity or condition number. Okay? If a matrix, let's talk about this. If I have a system A x equal to m, okay? X is the unknown vector, m is a known vector, A is a known matrix. If I like to solve this equation, okay, solve for x, what would you do? You will say A inverse of it equal to A, like this one, right? So this will go away, and this will be your x solution, right? So if A is a singular matrix, what does that mean? You cannot take the inverse of it, right? That's why singularity is important, right? Singularity is important. So by looking at these numbers, if sigma n is 0, then I know that this original matrix A is a singular matrix. Okay? If sigma n is 0, A is a singular matrix, you cannot take inverse of it. So there is no solution for this equation, for this linear system. That's nice, but we have something nicer than that, okay? Well, by looking at this matrix, when you say sigma n is not 0, for computer processing, not 0 doesn't mean that it is not exactly 0. Remember, they would tell you that never use real numbers or double numbers to represent money. Why would they say that? Why wouldn't you use double numbers to represent money?
Because the comparison might not hold every time.
Because the comparison might not hold every time. Because the real numbers are only approximate numbers, right? I mean, if I have 10 to the minus 9 Turkish liras, okay? Does that mean that I have 0 liras? Well, this is not different. This is not the same as 0. This is a very small number, but it is not 0, right? So this shouldn't happen. But in computer world, if you are using doubles, this sigma n could be very, very small number, maybe 10 to the minus 9. Should I accept this 10 to the minus 1 as 0 or not 0? What do you say? Well, if I take this as non-zero, and if I solve this equation that way by taking inverse of it, you might be hurting something, because you are working very, very close to your arithmetic precision of your floating numbers, right? That's not a good thing. That's why they say that if you are going to do something, if you are going to do some solution like that, just look at this condition number. Divide this sigma 1 by sigma n. If this number is large and if this is a very, very small, okay, this one is going to give you a very large number. If this large number is about your largest number representable, then you are in trouble numerically, okay? Although theoretically your sigma n might be different than 0, But for your computer system, for your processing system, you shouldn't continue. That's the condition number. Okay? Always check your condition number if you are solving these kind of matrices. If your condition number is close to your arithmetic precision limits, then you are doing something wrong. The results that you are going to get are not reliable results. Okay? Maybe you have some numerical degeneracy case. Let me write it here. Numerical degeneracy. Okay. That's one of the main problems of numerical analysis on computers. Theoretically, everything seems fine. Mathematically, everything works. But I mean, we are not doing exact mathematics on computer world, right? We say that I am dividing 1 over 3, right? I am dividing 1 by 3, and it says 0.3333, but that's not exact, right? That's not exact, and that's the problem with the numerical approximations. With the matrices, it's the same thing. So, given a matrix like this A, okay? Given the matrix A, do the singular value decomposition. Just check this number. If this number is comparable to your arithmetic limits of your numbers, then don't continue. Do something else. Okay? Condition number is something that I told you now about the singular value decomposition that is useful. The second one is the rank of a square matrix, or the rank of a matrix, any matrix. Okay? The rank of a matrix A is the number of non-zero singular values. So count this one. This is non-zero, non-zero, non-zero. If you have 5 non-zero elements in this matrix, then you say that the rank of matrix A is 5. Okay? So why is it important to have the rank of a matrix? Remember, what was the rank of the fundamental matrix? F. Do you remember the fundamental matrix song? At the beginning it starts with fundamental matrix. It is of rank what? It's a 3 by 3 matrix. It could be either 1 or 2 or 3, right? 3 is a full rank. So you did not listen to fundamental matrix song at home? It was so boring. Do I have it here? Oh, okay, here it is here. Okay, good. Run it.
The fundamental matrix used in stereogeometry, a matrix with 9 entries. It's square with size 3 by 3, has 7 degrees of freedom. It has a rank deficiency, it's only of rank 2.
Okay, its rank is 2. It's not 3. It's not you cannot solve. That's why, I mean, if you had a fundamental matrix of rank 3, then when you say point P times F, okay, times P2 equal to 0, if you had a full rank matrix F, then you couldn't get 0 here, okay? It has to be a different number, a non-zero number. In that case, you would solve that and you would say that P2 is this. You can definitely solve P2. Remember, we cannot solve P2 in this case because this would only produce a line that P2 can be on, right? That's why fundamental matrix has to be off rank, not full rank, but off rank 2, okay? So it is important to sometimes to measure and to know the ranks of matrices. And the singular value decomposition will tell you that the number of non-zero singular values will give the rank. So how is this useful for us? When we for example calculate the fundamental matrix or estimate the fundamental matrix, we are going to do the single value decomposition of that matrix, and we are going to force it to have a rank of 2 by turning the third element of that singular value to 0, and that will make it automatically of rank 2. So I can force a matrix to have a rank of 2. Okay, good. Oh, it looks like I'm out of time. Let me take some 15 minutes of break. After the break, I will come back and I will ask you more simpler questions, and I think I am going to get some answers from you. Okay, so let's be here around 16:40. Okay, so let's look at some other features, useful features of singular value decomposition. Actually, a singular value decomposition is so nice that anything you can do with a matrix, you can do it better with singular value decomposition almost always. We talked about the condition number, we talked about the rank. Let's look at the inverse of a matrix, okay? Let's say you have a matrix A, you like to take the inverse of it because taking the inverse of matrices is so useful, but it is difficult. So this is how you do the inverse of a matrix. You take the singular value decomposition like U, D, and V transpose, okay? And you take V, you put at the beginning, you put where did it go? Okay. This is the regular A U D V transpose, okay? You take V, you put at the beginning, okay? You put U at the end by taking transpose, and you multiply the inverse of D in between them. That will be the reverse inverse of matrix A, okay? So this is much easier. So how do you take the inverse of a diagonal matrix like this? How do you take the inverse of a diagonal matrix? It's just 1 over the diagonal elements, that's it, right? So if this is my matrix A, B, C, okay, these are all zeros. Inverse of it is 1 over A, 1 over B, and 1 over C. The rest of them is zeros. 0, 0, 0. This 0 is extra, right? So taking the inverse of a diagonal matrix is very easy. That's why once you do the singular value decomposition, this will be your inverse. Of course, taking the inverse means that your matrix has to be full rank, or it shouldn't be singular matrix, right? Because you are going to take the 1 over singular value. If the singular value is 0, then you are in trouble. For that case, I have this pseudo inverse of A, and it is shown as plus A plus. And again, the same thing, V U transpose. Instead of taking the 1 over singular values of all of them, you take 1 over singular values. For the zeros, you just take them as 0. Okay. If this C is 0, then put a 0 here. Don't take 1 over 0. Okay. That becomes the pseudo inverse of it. If your matrix doesn't have an inverse, you can still produce an approximate result, a good enough result, by, let's say, AX equal to B. You can do X is equal to A plus B. Okay? It is better than not having a solution. It's not going to be an exact solution. There might be many other solutions. Okay? But sometimes this kind of a solution is better than not having any solutions, and this will be very useful. Okay? This is called pseudo inverse of a matrix. And we will use that. Okay, let's come to the eigenvalues and eigenvectors. Remember the definition of the eigenvalues? Remember those? If I have AX, okay, lambda x. Remember, what was the significance of this equation? Remember this one? AX is such a special vector for this matrix A. Whatever this A is doing to this X, it's a transformation, right? This A is transforming X in a way that we are only growing that vector, either growing or shrinking that vector. That's it. We are not changing the direction of that vector. The direction of the vector stays the same. only we are moving along that direction. That's the definition of the eigenvalue problem. So this, okay, this X is an eigenvector for this matrix A, and this is an eigenvalue. Okay, remember this, we did this for the corner detection. It is very useful thing, and these eigenvalues and eigenvectors are characteristics of this matrix A. Okay, it tells you lots of things about these matrix A. If this matrix A has many eigenvectors and many eigenvalues, then it's kind of it contains lots of information. Okay, if you have a matrix like this, it's all 0, 0, zeros, n by n matrix. Okay, not a very interesting matrix. If you do the eigenvalue analysis of this matrix, you are not going to get any eigenvectors, eigenvalues. Okay, but if you have a matrix that you can solve for like n equations, that kind of stuff, you will see that it's a full matrix. Okay, its rank is full. It's not a singular matrix, and it has as many columns as it has singular values, singular. It has eigenvalues, eigenvectors whose number is the same as the number of columns and number of rows. And singular value decomposition, you can use the eigenvalue analysis. This is the case. Okay, remember this A is equal to U D V transpose. If you multiply A with A transpose, and if you multiply it with UI, you will get UI squared, sigma I squared UI. That means what? This is the eigenvector of this matrix, and this is the eigenvalue. So the singular values are the square roots of the eigenvalues of this AAT. And if I like to do the ATA, again, this time it is V's. Okay, V's and U's. Okay, so these are some nice features of the this singular value decomposition technique on the matrices. Okay, linear algebra is very important. Okay, linear algebra is usable in many fields of the computer science, also in many fields of the other science and engineering areas. You should know your linear algebra very well. You will never know. It will be very, very handy in some other problem that you will meet. Okay, linearization, linear things are very useful for us because we know how to solve them. Okay, including the linear systems. Okay, good. And what else is this? Okay, good. So let's get this one. You know the least squares estimation, right? If I have, let's say, unknown vector, known matrix, and known vector, okay, you like to solve for this X, and this is an overdetermined system. Let's say I have 3 unknowns, x1, x2, and x3, okay, but I have many equations. Okay, many equations, only 3 unknowns. So I need only 3 equations, but I have, let's say, 30 equations. You can just pick 3 equations out of the 30 and solve for x1, x2, x3, but I like to do it better than that. So least squares is one way of achieving this. You say that I am going to use all 30 of them, all 30 equations, and since they will not agree with each other for the solution, I am trying to find a solution that will minimize the error, total error of those equations. For these cases, we use the least squares, and there are ways to solve the least squares directly, or you can use, again, single value decomposition. What a surprise. Remember this one? When I say A x b is the equation I like to solve it, and this is what I do. I multiply A with AT, okay, and then this is what I would do. I multiply each side with ATA pseudo inverse, okay. So this side is isolated. X is equal to ATA pseudo inverse times ATB. So this is definitely a least square sense solution for X. So what are you going to do? You do the singular value decomposition, calculate ATA plus, and multiply it with AT and then B, and that will be your singular value solution for your least squares stuff. Okay. How to solve this? Compute to see the inverse of ATAD by singular value decomposition. Okay. ATA is more likely to coincide with the ATA minus 1 given m is greater than n. And these are all proven stuff. We are just using them. Okay. So least squares solution is one thing. Okay. We looked at all of that stuff just to come to this one. Remember, this is a homogeneous system. That's the definition of the homogeneous system. If you have a linear equation like this, matrix times x equal to 0, matrix times x is equal to 0, okay? This is called a homogeneous system. Why? Because if you find a solution x, I can multiply x with any constant k, and that's again another solution. Okay? That's again another solution. That's called homogeneous system. And remember, at the beginning, before I started talking about these single value decomposition stuff, okay, I did that. Okay, P is known, M is not known. If I multiply P with M, I will get a 0. This is a homogeneous system. If somebody says that I found an M, I can multiply that M by K, at that MK is another solution to the system. Okay, MK is another solution for the system. It's a homogeneous system. And we are going to use, well, what did I say again? The other thing that I told you, your regular Gaussian elimination or regular linear system solution techniques will solve the system, but usually they will produce you the trivial solution, which is 0. Okay? But I don't like that trivial solution. I like to use something else to find non-trivial solution, and singular value decomposition will help me in that case. Okay, I have m equations and n unknowns, and m is greater than n minus 1, and in this case the rank of this matrix has to be n minus 1, otherwise this equation will not hold. Okay, and if you like to make sure that rank of A is really n minus 1, just take the singular value decomposition of A and count the number of non-singular values. Okay, count the non-singular values, non-zero singular values, sorry. And if it is not n minus 1, then make it by force n minus 1. Make the last one 0 and multiply it again. Okay, a non-trivial solution by singular value decomposition, you just simply do this. Okay, you just simply do this. We know this, right? ATA VI is equal to singular value I square VI. That comes from the definition of the singular value decomposition. Okay, we say that our solution is simply proportional to the eigenvector corresponding to only 0 eigenvalue of ATA. Okay, so ATA has eigenvalues and eigenvectors. This Vn is going to be our solution. That's it. Okay, that's it. You just do the single value decomposition of A and take the remember U, D, V, take the last column of the matrix V, and that will be your non-trivial solution. That's the beauty of single value decomposition. That's it. So singular value decomposition of A. Take the V matrix, the last column will be your solution, non-trivial solution. Of course, this A has to be rank n minus 1. If it is not done, force it to be. Otherwise, just look at your data. And then this will be your solution. That's it. Okay, so that's how we are going to solve it. That's how we are going to solve this. Where is it? Yeah. Solve this equation. Take the singular value decomposition of P and take the last column of matrix V, and that will be your solution. Okay? How am I gonna take the single value decomposition of a matrix? Well, they teach you how to take the singular value decomposition of matrices, or maybe you can use the SVD procedures of OpenCV. See, this OpenCV has input array, okay? This is SRC, and output array is your solution. Output array U, output array VT, and this one. Okay, so decompose matrix. This is S source. This is the decomposed matrix is equal to, okay, calculated singular values W, okay, and calculated left singular vectors and calculated right singular vectors. So this is U and this is VT. Actually, VT is the transpose version of it. V and VT. V and VT are the same thing. One is a transpose version of it. Okay, dot and dot. That's it. And of course, there are ways of calculating the singular value decomposition thing, and you can see, okay, you can change the way how it is, but usually the default one is good. Okay, usually the default one is good. That's it. So OpenCV will help you to get those values. Any questions? Are we done? Are we done with the camera calibration? Are we done with the camera calibration? Once you solve this equation, P times equal to M0. Decompose this P into 3 and take the last column of V, and you have your M values. But are we done? The answer is of course no. Why? Because I have half an hour left and I need to spend that time for getting to the end. No, we are not done. What are we going to do? We have only found these 12 numbers. Okay? I have only found these 12 numbers. By the way, whatever I found as an M, if I multiply that M, K times M, that's another projection matrix. Okay? So doesn't matter what kind of M I am finding. Multiply with K. Of course, K should not be equal to 0. Okay? I have another M, which I don't like. Why? Because if I found these 12 numbers, what is this TZ? My right corner value is TZ. Is that correct? The answer is no. Because I found this M dependent on this K value, and I don't know what K is actually. Okay? I found an M that contains 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 12 numbers. You might say that this one will correspond to this one. Yeah, but TZ times K is this value, and I don't know the K. Again, are these three values the same as R3? The answer is, well, it is K times R3 are these values. I don't know what the value of K is. Okay? So I am not done, and if I am not done with these last row, I have many more things to do with these 3 rows. So let's see what kind of mathematical tricks we can do to find those. Okay? So I found M. Inside them, I have 3 by 3 A matrix and 3 element vector B. Okay, so I know that this rho times A, B, rho is a scalar, is equal to KRT. Why? Because I don't know this constant rho. Okay, and I can write this maybe. Let's take this A. Okay, let's take the rows of A and transform them into this A1T, A2T, and A3. So it's going to be equal to this 3 by 3 matrix. This is what I am after, but all I have is this rho times these values. Okay? So let's look at this last row. So last row is rho times A3. I know that if I multiply R3 transpose with R3, I should get 1, right? That's the definition of the rotation. I know that one. But I don't know what R3 is. All I have is rho times R3, which is this one. So that's what I'm going to do. Rho times R3 times rho times R3 transpose is going to give me 1 times rho square, right? That's what you guys can't read anything? Why don't you tell me? You don't care? Okay. So I told you that R3 times R3 transpose is going to give you 1. I know this one because of the orthogonality. I don't know R3, but I know rho times R3 times rho times R3 transpose is going to give me rho square times 1. Okay, so if I multiply the third row of this matrix A by itself, it's going to give me rho square. Okay, and if I take the square root of this rho square, it's going to give me rho. Is that correct? If I take the square root of rho square, it's going to give me rho. Is that correct? The answer is no. Why not? It's going to give you absolute value of rho, right? So there is I found rho, but I didn't find the exact rho. There is a minus plus factor in it. Okay? I just took the absolute value of rho. Okay? So let's continue and let's see if I can find the absolute value of the signature of rho somewhere, and we will do that. Okay? So you remember this already. The rotation around the z-axis, rotation transformation. And in fact, if I multiply this by itself, just multiply it by itself. Cosine square theta plus sine square theta plus 0. You guys remember this, right?
1.
Well, 3 people said 1. Okay, good. The first answer from today, without pushing it. Okay, so the same thing is here. Sine square plus the cosine square is going to be 1, and this one is going to be 1. Doesn't matter. Do the same thing here. Rows and columns. So that's the property of the rotation. Okay. Okay, so remember this is our A matrix. I am after this R3, but all I have is this rho times A3. So our rho is going to be again, if I multiply this, R3 is by itself. Okay, that's going to be rho times A3 is going to be my R3. How about these two? Where did I get these two? Somebody tell me these two. U0 and V0, they say that multiply this one with A1 and with this one. No, you can't see that. You can with this one, right? You will get U0. How could that happen? What is rho times A1? Okay, it is multiply A1 with R3. Let's multiply it. If I multiply R3 with this one, it's going to produce what? If you multiply R3 with R1, what is R? It is first column, second column, third column. If you multiply R1 with R3, what would you get? If you multiply this one with this one, what would you get? No. If you multiply this one, this row with this row, or this column with this column, what would you get? 0, of course. These are orthogonal, right? These are orthogonal. So if I multiply R3 with R1, it is 0. If I multiply R3 with R2, it is 0. If I multiply R3 with R3 again, right? R3 and R3 is going to be 1. So if I multiply this one with this one, including the row term, you are going to get rho square, okay, A1, A3 is going to give you U0. Okay? It's going to give you U0. Do I know what rho square is? I know the absolute value of rho. Okay? If you take the square of it, I know the rho square. Yeah? I know the rho square. So I know A1, A3. It comes from there. Okay, I multiply them, and I multiply with rho square, you get U0. And the same thing is, again, multiply with this is 1, this is 0, and you get V0. So congratulations, you obtain your first parameters from this equation set, which is U0 and V0. Okay, you know the V0 and V0. You might say that, well, I know R3 too, but you know R3 depending on the sign of this row. I know the absolute value of rho, but not the sign of it. So sign depends on the -1 + 1. Okay, just a mathematical trick, that's it. It all depends on this orthogonality of this matrix R. Okay, so what else do we know? Okay, kind of solve this one. V0 and U0 are there. Let's play this trick again. I know that R1 times R2 is 0, right? I know this. How about this? R1, R2, cross product. If you cross product two orthogonal vectors, it's going to give you another vector which is orthogonal to both of them, right? Which is what? Which is R3, right? Good. So I can play with this. How about this one? R1 cross product R1. Do you remember from your high school? Or from 2 to 3 weeks ago I told you this? Remember the homogeneous coordinate systems? If you cross product a vector by itself, it's going to give you a 0, right? So using these properties, we are going to play a few more tricks. Okay. If I multiply A1 with A3, this one with this one, using the cross product. So A1, A3, R3, R1 is going to give me minus R2, alpha times minus R2. R3, R2 is going to give me R1 minus theta cotangent alpha cotangent theta R1 and R3 is 0. Okay, so cross product of these two vectors is going to give me this. Cross product of these two vectors, this will be 0, this will be R3, R2 is going to give me R1. Okay, R1 beta over sine theta. And if I take the absolute value of this A1, A3, so take the square of it and take this. If I multiply this by itself, okay, if I multiply it by itself, a vector, so R1s and R2s, they will cancel each other, and you are going to end up with this value theta, alpha over sine theta, and take the square of it, beta over sine theta. So what are we doing? What are we doing? Well, let's get this one. Take this value, multiply it with this value, R1s will go away, okay, divide them with these, all you are going to end up is going to be this cosine of theta. Cosine of theta, I know, it will be this, okay. Once you know the cosine of an angle, you know the sine of it. Once you know the sine of it, I can calculate this alpha and beta values because of these. Okay, so I know now the theta, alpha and beta values. Okay, I know theta, alpha and beta values. Previously u0 and v0 I recovered. So how many parameters I know now? I know 1, 2, 3, 4, 5, and also I know the R3 depending on the sign of the row, which I don't know. Okay. Again, doing the same kind of tricks. Doing the same kind of tricks. I will do this. This one. Okay. This one is going to give me. This one is going to give me alpha R2, alpha cotangent R1. I know alpha value, I know the beta value, I know the theta values, so I know this, I know this and that, right? I know those. Okay? If I know those, oh sorry, I'm looking at this one. I know this one and this one. In that case, I can figure out this R1. R1 is there. Okay. If you know R1 and if those values, you can get R2. Okay. And or if I cross product R1 with R3, you can get R2. We know all those. So I know all of them, R2, R3, and R1. But still, I didn't figure out the sign of this row value. For that one, we are going to use this trick. Remember this KRT equation set. For the T, I have Tx, Ty, and Tz vector at the end. Okay. Just test all these values that have discovered, that have estimated, with a plus row value or the minus row value. Whichever makes this Tz positive, because Tz has to be positive. Okay? Tz has to be positive because my camera system, remember, it is like this. Okay? X, Y, and my image plane somewhere like that. Okay? My Z has to be a growing Z. It cannot be a negative one. So put all these values and make your row minus and plus. Whichever makes my Tz plus, that will be your row value. And that's how you end up finding the sign of the row value. And that's it. So So we have calculated all those R1, R2, R3 rotation matrices. Okay. TZ is already there. TZ is already there. And since I have calculated all of these parameters, where is my... Okay, let me go to this one. Since I have calculated all of my R1, R2, R3, alpha, beta stuff, okay, now I can calculate TZ with the known stuff. Since I know TZ and V0, beta, and theta, I can calculate TY. Since I know TZ, TY, I can calculate TX. All of them are now done. So in total, I have calculated 3 translation parameters, 3 rotation parameters, 3 rows of it, U0, V0, alpha, beta, and theta. Okay, so my calibration is done, but before I give up, before I said I am done, maybe I should say, well, didn't I say that my rotation matrix is orthogonal? Yes. So I have recovered these 9 parameters of this rotation matrix, right? How do I know that if I take the transpose of it and multiply it, I would get an identity matrix? How do I know that? Just try it. Since you have numerical errors, you have measurement errors and that kind of stuff, you will not get a perfect identity matrix. Okay? It will not be possible. It will be around 1 zeros. It will be something like 0.99 something, 1.0001 something, and these are not like 0.2 to the minus 9, 10 to the minus 3, very close to 0, very close to 1, but it's not perfect identity matrix. So what you're going to do is do the singular value decomposition of the matrix that you have obtained. Okay, singular value decomposition says that if you have an orthogonal matrix, your diagonal matrix should be 1, 1, 1, 0, 0, 0, 0, 0, 0. Okay, so just replace whatever you get from the singular value decomposition with this identity matrix and multiply it together and make a new R. I definitely know that this R is an orthogonal matrix now. Okay, it both conforms to the constraints of the linear system that we have solved, and by using the singular value decomposition, I also know that R is an orthogonal matrix. Okay, so that's basically it. This is how you do the camera calibration. Let me go back, and this is how we started. Get a target like this, buy it from somewhere. It's not that expensive. Buy it somewhere and get an image of it and do all these calculations, and you are going to get your results back. Okay, and by the way, this is the simple ways of doing it. Mathematically, this is simpler than the alternative methods. More involved and more mathematically, well, it is not difficult, but it will take me a few weeks to tell you how it is done. OpenCV does it in a different way. OpenCV does it this way for the camera calibration. It says that print a checkerboard pattern like this on a plain paper and put this on a planar book. It has to be rigid. Show this to your camera using different orientations, different angles, and different positions. Okay. Then, well, I will assume that your first image has this 0, 0, 0 point. Okay. Your X is here, Y is here, and Z is here. Okay. Your first image will give me your origin of the real world, and your other images will live in that world, but your corner is not 0, 0 anymore. Okay, define a real world coordinates of 3D using checkerboard pattern. Capture the images of the checkerboard from different viewpoints, different angles, and etc. As many as possible. And find the corners of it using the find chessboard corners method. And then after that, you call this function calibrate camera. Okay, it will give you object points, and then image points, image size, and it will be your output array, camera matrix, distortion coefficients. Remember in this case I didn't give you the distortion coefficients. Remember our last distortion coefficients, the radial distortion coefficients. This one is going to give you that too. Rotation vectors, 9 numbers, and translation vector, 3 numbers. So calibrate camera will give you this. Again, OpenCV has lots of other procedures, like I have my intrinsic parameters, like give me the extrinsic parameters, etc. Okay, so you can say that I know this one, okay, I know this one, give me these two. That's why, see, that's why these are not input arrays. That's why these are input output array. It could be other. I am giving it to you and I want it back, or I am giving it to you, I don't want these to be calculated, I only want these R back and T back output array. Okay, so as I said, OpenCV, the procedure is, as an end user, for the end user it is much simpler, because you don't need to buy any calibration targets. You print this out and you show this your camera a number of times with different orientations. That will be it. But the method that I told you requires this target, and you are supposed to take just one image of this target. Both this thing is a costly thing, you need to buy it, not that convenient. Also, you need to take very special angle picture of it. With the OpenCV implementation, no, you don't have to buy anything. You just show as many images as possible to your camera and calculate the corners and feed them to your calibrate camera routine. That's it. Okay, camera calibration. If you know your camera calibration routine, if you know your K and R values, KRT, remember this one. M is equal to K, R, and T. Okay, if you know all of them, K and R and T, of course, if you have two cameras to your setup, left camera and right camera, if you know both of them, K1, R1, T1, K2, R2, T2, remember I gave you the formulas. You can calculate your essential matrix or fundamental matrix out of those. Or if you know your projection matrices, remember the triangulation method and the linear method to estimate your XYZ values. You can get those too. So it is directly connected to your stereo estimation routines too. Okay? And mathematically everything is very simple if you use a singular value decomposition. Now my suggestion to you is go home and look up your linear algebra notes and see how you did the singular value decomposition and the proofs of it. Good, that's it from me for this week. Are there any questions? No questions? You understood everything? And that's fine. Good. Okay, thank you. Then I will see you next week.